Welcome back to The Explainer. Today, we're plugging into the world of electronics. We're going to demystify the whole thing, from the gear you find on a workbench all the way to the big ideas that power our world. All right, let's just dive right in. When you first look at an electric circuit, it can seem like this incredibly complex, almost chaotic maze of lines and symbols. But here's the thing, it's not chaos at all. It's actually a system with its own language, its own rules, and a logic all its own.
So that's the big question, isn't it? How do you make that jump? How do we go from just staring at these lines to actually understanding what's happening inside them? How do we learn to speak the language of circuits?
Well, to answer that, we've got to start by grounding ourselves in the real world. Before we can even touch the theory, we need to get to know the place where all that theory becomes reality, the electronics workbench.
Because let's be real, electronics is a hands-on thing. It's all about building stuff, testing it, and measuring what's going on. And to do any of that, you need a very specific set of tools. Okay, so let's gear up. We're going to take a look at the core equipment, the absolute must-haves that every single electronics lab needs to get anything done.
The experts will tell you that it all boils down to these 6 key pieces of gear. As you can see, we've got tools for measuring, tools for seeing signals, for providing power, and for physically putting our circuits together. These are the things that let us actually interact with and understand what's really going on. First up, the multimeter. Seriously, think of this thing as the Sherlock Holmes of your workbench. It's your go-to tool for measuring those 3 big electrical properties: voltage, current, and resistance. And it is absolutely essential for figuring out what's wrong with the circuit. And it's pretty mild to think about the history here. Our modern digital multimeters all evolved from these really elegant mechanical ideas, like this one, where a current flowing through a coil would literally move a physical needle to give you a reading. Simple, but brilliant.
Okay, a multimeter gives you a number. Great, but what if you need to actually see what the electricity is doing? For that, you need an oscilloscope. This is a staple in any lab. It literally draws you a picture of a signal's voltage as it changes over time, so you can see its exact shape.
And of course, none of this works if you can't power it up, right? A regulated DC power supply is critical for just about any test you can think of. It gives you the stable, controlled energy you need to bring a circuit to life without, blowing it up. All right, so we've got the tools. Now it's time to learn the language they actually measure. We're talking about the 3 big concepts that describe everything in a circuit: voltage, which you can think of as the push, current, the flow, and resistance, the thing that pushes back against that flow. But before we get into those, we have to make one super important distinction. There are 2 basic ways electricity flows. You've got direct current, or DC, which is that steady, constant flow you get from something like a battery. And then there's alternating current, or AC, which zips back and forth. That's what comes out of a household wall outlet. So the first pillar of our language is voltage. You can basically think of it as the electrical pressure in a system. It's the force that's pushing all that electric charge to get it moving. And its unit, the volt, is named after a real pioneer. And this is the guy we have to thank for it, the Italian physicist Alessandro Volta. Way back in 1796, he invented the electric battery, and that, for the very first time, gave us a continuous, steady flow of electricity. It was a breakthrough that completely changed the world. Now, what's so cool about this is that Volta's invention wasn't just some new device. It was the spark, no pun intended, for a whole new field of science. The ability to create a steady flow of electricity is what made the entire theory of electric circuits possible. So if voltage is the pressure, then current is the actual flow. It's the measure of how much charge is moving past a certain point in the circuit in a given amount of time. It's what happens when the voltage does its pushing. Okay, so we've got the tools to measure and we have the language to describe what we're measuring. Now we need the grammar, the fundamental law that connects all these ideas and really makes circuit analysis happen. And that brings us to Ohm's law. This was discovered by the German physicist Georg Simon Ohm. And this one simple relationship is the absolute cornerstone of circuit analysis. It's the bridge that connects voltage and current to that third piece of the puzzle, resistance. The entire relationship is captured in this incredibly elegant and powerful equation: voltage equals current times resistance. This simple little formula is one of the most fundamental and widely used principles in all of electrical engineering. It's that important. And this shows you how engineers actually apply laws like Ohm's. See, it's not just about mindlessly plugging numbers into a formula. It's about a structured, repeatable process. You define the problem, you look at your options, you try a solution, and then you rigorously check your work to make sure you got it right. So you might be wondering, why does mastering all these fundamentals matter so much? Well, it's because these simple concepts, voltage, current, resistance, and the law that ties them together, are the absolute building blocks of all modern technology, period. I mean, think about it. From the ignition circuit that starts your car, to the airbag that could save your life, to the massive power grid that lights up our cities, these basic principles are at work absolutely everywhere, in tons of things we rely on every single day. And that's really the key takeaway here. Understanding these fundamentals is just the first step. From that simple workbench to the most complex technology, these are the building blocks. They are the foundation for a whole lifelong journey of learning and innovation. So the real question isn't just, how does a circuit work? It's, what will you build with it?